Yeah, hello. Good evening. Good evening. Am I audible?
Yes, sir.
Have you got your quiz one result yet?
Got it.
No, sir, I don't think so.
You got it. Some of you may have
Yes.
got it, no? How was it? Rohit, have you got it?
Yes.
Yeah, how was it?
It's pretty good.
I mean, was it as expected as you have done?
Yes, sir. It was expected.
Okay. Yeah, anyone else who has got result? Quiz one result? No? Okay. And so last live session, I think most of week 8 concept were discussed, right? Okay. Can someone tell me what an inner product is? Anyone? Am I audible?
Yes, sir.
Yes, sir.
Yeah, so can someone tell me what an inner product is, or what do you understand when you hear the topic inner product? What is meant by that?
It is
It
from
is a
Huh.
it is a vector space defined on an inner product.
Vector space defined on an inner product,
In
or inner product defined on a vector space,
inner product defined on a vector space,
right?
which
And
has
what
four
is an inner product?
inner product is a such that V cross V. It is a dot product actually.
Will it always be a dot product?
No, it's always not a dot product.
Okay, okay. So yeah, it is like something like dot product then.
Yes.
Uh,
So
and
when
what does it capture?
it captures four properties: positivity, linearity, symmetricity, and
Hmm.
Yes, sir. The bilinear properties.
That is basically the axioms for inner product, right? When a function, so inner product is basically a function, right? From G
it
cross
is a
V
function.
to
Yes.
R, and it satisfies those four property, the bilinear property, as you are saying. Now, why we need inner product at all? Any idea of that? Why we actually need inner product? You have seen most of Wicket chapter, Wicket concept, right? What you have learned in Wicket, you have a vague idea of that. Now, why? I mean, what is the use of reading inner product?
Hello, sir.
Yeah.
Bilinearity means that plus condition as well as that multiplication condition, both inclusive in that.
Can you speak a little bit louder?
Hello.
Yeah.
Bilinearity means that plus condition and multiplication condition both are inclusive in that, right?
So those are basically axioms of inner products. I am asking why we need the inner product at all. That is my question. And
Okay.
why we use inner product, right? So when we start learning anything, the first question arises that, I mean, why we are learning it? So, any idea why we are doing inner product? So at the beginning in week 7 actually, we have seen that there is something called dot product, right?
Yes, sir.
Yes, sir.
Yes.
What does dot product do?
Coordinate wise multiplication and adding.
That is how we do calculate dot product. But what its implication? If I do dot product of two vector, what do I get?
We get a scalar.
We get a scalar, and what does that scalar represent? Is
That
it any arbitrary scalar or it has some meaning?
yes, sir, it has meaning.
What, what that meaning is?
Uh, it is the dis-
Hmm. Anyone else wants to try? So the question is, what does dot product captures?
Sir, both the spaces which we use to find in a product, it captures the both.
Capture both vectors.
Yeah.
Is it? How? I mean, we do dot product of two vector and we get a scalar. Now, what that scalar really gives us? Or it is just an output, we don't really bother about that. Is it like that? Yeah.
Sir, that scalar is basically the length of those two vectors into cos theta, into the angle between them.
So somehow
Yes,
it
sir.
captures the angle between them, right? Yeah. So it captures the positioning of those two vectors, how they are situated in our vector space, right? Correct. So inner product does the same thing with more generality. That is the first thing we need to know, right? So if I this, this can you see my screen?
yes,
Yeah. So basically, here I have written the points of the inner product, the axioms of the inner product. Right? So we have vector space with some operation. We don't know what operation the vector space has, right? But it has addition. Somehow it is defined, and scalar multiplication that we know because this is a vector space. Now we are creating a function, right, from V cross V to R. So what is V cross V? It is the Cartesian product of two vector spaces, right? So all possible pairs with the elements from V. And we are creating a map to a real number. Basically, we are getting a scalar. And as we have seen that in case of dot product, we captures the angle between them. So this basically gives us more generalization of that. Okay. And at the later portion of the chapter, we will come to see that it somehow helps to calculate the projection. So that is the thing I wanted to hear. Okay. So inner product basically helps us to capture the projection. And we know the projection
But
has
sir,
many applications,
how
right?
inner product is related to that
Yeah.
angle between two vectors? Because it's defined as the dot product divided by uh, the length of those
Hmm.
vectors. But we can define our inner product.
Right. So dot product
Yes, sir. Yes, sir.
in some other way, right? That is what you are saying.
Yes, sir.
Yeah. So I am saying that this inner product is basically a generalization of that because if you see dot product, that will also satisfy these four property, right? Because dot product is an inner product, correct? Is it not clear? So suppose I have two vectors. Let's start with. So let's take V as R2. Okay. And I have two vector V1 and V2. So V1 is x1, y1, and V2 is x2, y2. How we define dot product V1 dot V2? How we have defined that?
X1,
X1
X2
into x
plus
y1
Y1,
into
Y1, Y2.
Correct.
standard
This
dot
is
product.
standard dot product. Yeah. So this is what we known by dot product, right? And so if I, so this is also, I can write it like this. So a map from V cross V to R, correct? Here this V is my R2. This is also R2, correct? And I am taking two vector V1 and V2. And that's how I am defining my map, correct? Now, to check whether it is an inner product or not, what I have to check first?
B comma B should be greater than equal to 0.
0. Is it satisfying that property?
Yes, sir. It is satisfying.
So is it clear to everyone? So if I take v as my x comma y, any vector. So what is v? It is
It is 0 if B is
v dot
0.
v, right? So if it is v dot v, that means what? That means if I use this formula, I mean how the dot product is defined, it
S
will give
comma y
me
dot s comma y dot x square plus
correct.
y square.
Exactly. Right? Now can it be negative?
No.
No.
It can never be negative, right? It is sum of two positive real numbers. So it can never be negative. So it is always greater than equal to 0. Correct? And when it is 0?
When x and y both are 0.
Correct. If x square plus y square is 0, then they both must be 0. So what is our vector? 0 comma 0. Correct? And that was our first axiom, right?
Yes, sir.
If I see our first axiom, the inner product of two same vectors is always greater than 0 if v not 0, and inner product is 0 if and only v is 0. And that is what we are getting, right? So if v is 0, what is the dot product of it? What is v dot v?
0.
It is 0.
0.
So this satisfies, right? V is 0 if and only the inner product is 0. Right? This is the first axiom. Now, does this satisfy the second axiom? What was the second one? Second one was linearity, right? Linearity with respect to the first coordinate.
Sir, this is called as bilinearity or linearity.
Correct. This is called bilinearity because there are two coordinates. So I am saying linearity with respect to first coordinate, right?
No, I was asking earlier that second condition and fourth condition both should be satisfied is called as bilinearity, or that second condition name is bilinearity.
I'm not getting what you are saying. This
So
altogether is called bilinearity.
Sir, the third condition is that c into v dot u dot v is equal to.
Fourth
Uh,
condition.
Yes,
Fourth
that is the third condition. So third and fourth both are same. We call it as linear bilinearity, or that is
Sir,
Sir,
second and fourth
I
together
think
we
all
call
three
bilinearity.
conditions. Okay.
no, last one is symmetricity.
But we need that.
No,
Yes,
third is symmetry.
We need that. So
Okay.
what
No,
basically?
sir.
Let me.
What is bilinearity?
I am saying that.
Oh, yes, third is symmetry. You are right.
Suppose I have this. Okay. If it is commutative, right? What I can write? I can write this also. Correct. Correct.
Yes, sir.
By symmetricity. Correct. Now, if I break it down with respect to first coordinate, what does it mean?
Dot product of v1 v3 plus v2.
Correct. Now, if I use the symmetricity property in each of it, what will I get?
B3 B1 plus B3 B2.
Correct. So if I, instead of writing with respect to first coordinate, if I write with respect to second coordinate, will I get the same thing? Am I getting the same thing or not?
Yes, sir.
Correct. So what bilinearity basically means? Linear with respect to both the coordinates, right? So coordinates here, I mean, this is the first one. So if I say this one, this is the first one, this is the second one, right? So linear with respect to both the coordinate, right? This is called bilinearity property. So second and third together forms the bilinearity property. Is it clear? And this is what bilinearity actually means. This is the definition of bilinearity. Linear with respect to both the coordinates. Is it clear?
Yes.
Sir, but on what basis you flip that v3 comma v1 plus v2?
Symmetricity, no?
But it is not inner. We are yet to prove that it is inner product.
I am saying the second and third coordinate, third axiom, these two together says that it is called bilinearity. These 2 and 3 together is bilinearity property. Gives us the bilinearity property. Okay. Okay.
Okay.
So bilinearity means it should be linear with respect to both the coordinates. Okay. So suppose, so forget about inner product. Okay, bilinearity comes at many places. Suppose I have any map, okay, from two set A cross B to something here. Suppose C. Okay, so I have two coordinate in this place, right? F of A, B. It is going to somewhere, right? Somewhere in C, somewhere it is defined. Correct. Now, when I will call this function as bilinear function, when f is bilinear, that is what you are asking, right?
Yes.
Right. Now, I am saying f is bilinear if f is linear with respect to both the coordinate. Okay. What does it mean? If I have this a1 plus a2 only with respect to first coordinate, it should give us this. This is linear with respect to first coordinate, right? No issue in that.
Okay.
And if I have this one, this is called linear with respect to second coordinate. Correct? And if I have both these together, then I will call f as bilinear function. Is it clear what bilinear actually means? Correct? Any
Okay.
doubt in this?
Okay.
Okay. Now
Not the
come back to
fourth,
the
for only second and third by.
because only we are talking about linearity, not the scalar multiple of that. Right? Yeah. So this is what bilinearity means, right? Is it clear to everyone?
Yes, sir. So, sir, can we say that this inner product is a linear transformation?
Linear transformation means what? So there was a definition of linear transformation. Basically, I was going to come to that. So linear transformation means what? Linear transformation means it was a function from a vector space to vector space, correct?
Yes, sir.
V to W, which is linear, which was linear and respects scalar multiplicity, right?
Yes, sir.
So basically, I had these two things, V1 plus V2, which breaks down to TV1 plus TV2, and TCV is same as CTV, correct? Now,
Yes, sir.
here my domain is basically Cartesian product of two vector spaces, and W is real number. So that is itself is a vector space. That is fine. But the point is here I have V as a Cartesian product of two vector spaces, V cross V, which are same, but they are Cartesian product of two, right? So here, if
Yes,
we
sir.
need the same type of property as we are expecting in case of linear transformation, what we need? We need it should be linear with respect to both the coordinate, correct? And it satisfies the scalar multiplication property, right?
Sir, what you said, it should be linear to both the
Both
V.
the coordinate, right?
Yes. Okay.
That is what bilinearity means. Now, here, with over than bilinearity, scalar multiplication is also needed, correct? Because we are working in vector space. That's why the fourth axiom came, right? That's what where the fourth axiom came in the picture. So if I break it down, suppose what was the third axiom? This was third, right? Was not this discussed in the earlier live session? I thought it was discussed, no?
Yes, sir, it was discussed.
Huh. So this is the third one. And fourth one is basically again with respect to the first coordinate we are seeing. Correct? Now, a question which must come to your mind is what happened with the second coordinate? Because the second axiom and fourth axiom are basically talking about the first coordinate. Why are not we talking about the second coordinate? Correct? Because this is the second property is basically linearity with respect to first coordinate, right? As I have mentioned. Now, what about the second coordinate? Basically, if we have this third property, the symmetricity, this is called symmetricity. If we have this one, we really don't have to talk about the second one because that is inherited. If we have second and third together, we really don't have to bother about the linearity of second coordinate. That is what I was showing. Suppose I have here this. What I can do? I have symmetricity. I have said I have second and third together, right? So what I can write it? I can write it like this. Correct? Is this clear
Yes,
to
sir.
everyone that I am writing this step? Okay. Now what I have to do? We know the linearity with respect to first coordinate is there. So I can break it down. Correct? Till this it is okay to everyone?
Yes, sir.
Okay. Now what is V2 comma V1? I have symmetricity, you know. So I can reverse it. And I can also reverse this one because we have symmetricity. So is not it basically linearity with respect to second one? Correct? Is it clear?
Yes, sir. It is clear.
Okay. Now what about the fourth axiom? Is it also scalar? I mean, it is also respect scalar multiplication with respect to the second coordinate. Suppose I have V1 C V2.
You'll get
What I will get?
CV2 comma B1.
Correct. Because again, I can using the symmetricity, I can write it is as CV2 comma V1. Then I can take C outside. It is V2 comma V1, and I can again revert it back. So I am getting V1 V2. Correct. So this is also true with respect to second coordinate. So symmetricity basically gives us the bilinearity with respect to the second axiom, and the scalar multiplication will also respect with respect to second coordinate using symmetricity.
So what is the
Is
name
it
of
clear?
the fourth property, sir?
I mean, it is there is no such name as such. So it is called respecting scalar multiplication. The function, the inner product respects scalar multiplication. That's what we call it. Inner product. So if you want to write it in words, we write inner product respects scalar multiplication.
Sir, there are three names in the activity question: positivity condition, symmetry condition, and bilinearity. But here
Correct.
are four exams. Then
Bilinearity.
three names and four exams. That's why I was asking.
But now is it clear? I mean, what basically going behind this? Is it clear?
Sir, in
Huh.
the question, if they ask us to prove the bilinearity, then we should prove second and third property, sir. Is it enough?
Second, third, and fourth also. Because when we are talking inside vector space, I am saying the respect of scalar product is also included. No? That's why. I mean, so which question are you talking about? Can you tell me? Otherwise, maybe some misunderstood will happen.
No, sir.
Which question are you talking about?
General question, sir.
What is the question?
if they give us an inner product and they ask us to prove whether it is bilinear.
No, I mean inner product is always bilinear, right? Now, if the question is given, it will be given that check the linearity property or check the symmetry property or check the bilinearity property. It may come, but if you prove the bilinear property,
No, sir.
itself becoming an inner product,
It is not inner.
right?
Given that it is inner product, sir. Without that.
Hello, sir. It is 7.4 question 1.
Okay, let me see. 7.4 question.
Excuse me, sir.
Yeah.
Where is the YouTube link, sir?
Today it is not streamed. I will upload it after recording. Okay.
Okay, sir. Because I asked, I late for 25 minutes. So,
I will upload it anyway. I am recording the session, so I will upload it.
okay, sir. Thank you.
Yeah.
And what's going on, sir?
Definition of inner product. Okay.
Okay.
Yeah. Yeah. Which one are you talking about?
First question, second option.
So here, if satisfies only binary property, it is given, right? So you have to check only bilinearity, linear with respect to both the coordinate. Okay.
So second, third, and
Linear
fourth
with respect
property
to
you have
both
to
the
check, sir.
only second and third is enough here.
Okay, sir.
It is bilinearity condition, no? So it is linear with respect to both the coordinate. That is called bilinearity. That is what I have said. No?
Excuse me, sir.
No, sir. You said second, third, and fourth.
Second, third, and fourth all together will give the inner product.
And for bilinearity, second and third.
Second and third is enough.
Okay.
Okay?
Okay.
Okay. Fine. Is it clear to everyone? So here again I am mentioning this. A function
Sir,
is
one
called
small
bilinear.
request, sir. Sir, one small request. Sir, I think tomorrow is the assignment submission for week 8, and sir, we are discussing week
Right.
7. And sir,
No, I
tomorrow
am
is the
discussing
deadline.
week 8. I am going there step by step. Okay, I will cover. Anyway, week 8 is already covered, I think, in the last live session. No?
No, sir, no, sir. It was not covered at all.
It was covered,
The
sir.
No, it was covered. I have seen the session.
total
last
part was
is
not
remaining.
sir. Sir, Gram-Schmidt
Gram-Schmidt.
was removed. Yes, sir.
Yeah, okay, I will discuss that. Okay.
Yes.
Okay. Yeah. So just to mention this one, if function is bilinear, if it is linear with respect to both the coordinate, right? Only this much we have to check. So if we check only second and third property of the axiom which I have mentioned here, that is enough for checking bilinearity. Is it clear? These two, basically these two. Is it clear to everyone?
Yes, sir.
No? Okay. Amruta, is it clear?
Yes, sir. Yes, clear.
Okay, great. Okay, so basically these are the things we call, and all if a function satisfies all the 4 properties, then we call it an inner product, right? And now you can check. So I have taken some question. So suppose I want to check for the second one, right? My vector product is matrix 2 cross 2 matrices, and I am giving you the trace. Will it be an inner product? Is trace an inner product? Trace of product of 2 matrices? So basically, what
Yes,
I
sir,
am
it
getting,
is.
it is inner product, right?
Sure, sir.
Are you
Yes,
sure?
sir.
You have done this, okay. So let me see. So V is my M2 cross 2R. So how it is defined? Take AB, and I am defining it as trace of AB, correct? Right. So basically, if I take A of A and A, trace of A and A should be greater than equal to 0. Is it always true? is it always greater than 0? Is trace AA or trace of A square maybe? Is it
Yes, sir.
always greater than 0? Is it necessary?
Yes, sir. Yes, sir. It will always greater than 0 is.
Okay. So let me write it A, B, C, D and A, B, C, D. Now, if I write it down, what I am getting? A square plus BC here. And what I am getting in this corner is BC plus D square, right? So what is trace? Trace of A square. I am getting A square plus 2BC plus D square, right?
Yes,
Yes,
sir.
sir.
So you are saying this is always greater
No,
than
sir.
0. Then why you have said that?
I thought A square. I did.
How we have proved it then? But you had a proof, right? How have you proved that? So if I take this matrix, so I am considering these two as 0, let's say 0, 0, and say B as -1, and this as say minus +1, let's say this one. This is my A. This is my A, what is my A square? So this is what this is 0 and -1, and this is, and what about this position? -1, right? So what is trace? -2.
Yes, sir. It's negative.
It's negative. So it is not satisfying the first property, right? So this is not an inner product. Is it clear to everyone?
Yes, sir.
Who have said that he has done this proof and he has proved that this is an inner product? Have you realized where you have done the mistake? Huh?
Yes, sir.
Is it clear to everyone that this is not an inner product?
Yes, sir. It's
This
clear.
is not an inner product. Yeah, correct. So this is not an inner product. That's the main thing. So in this situation, you just write down what actually you are getting and try to find that whether this is actually greater than 0 or not, and whether you can construct some example. So you see how I am constructing the example, right? I have written down what is trace of A square. Now I had to somehow I have to make this negative so that A is some matrix, some non-zero matrix. I wanted that. So what I have done, I have made A and D as 0 because these are positive. I don't need that 0. If I make this product of B and C as negative, then I am done. That is how I have constructed the example. Is it clear? How we have constructed the example? This should be in your hand, in your practice, right? What about the third one then? Is it an inner product? The third one. So here, what I have written, it is M2 cross 1R, right? 2 rows, 1 column. Okay? So a 2 cross 1 vector, basically. And I am taking trace of A, B transpose. So how I am getting it? So let me just write V is M2 cross 1R. Right? And because V2R is defined as AB, in a part of AB, that is trace of AB transpose. So I am taking B as say A1, A2. So this is a 2 cross 1, right? And B as B1, B2. What is AB transpose? A1, A2 transpose means B1, B2. What I am getting is, so it is 2 cross 1, which is 1 cross 2.
2 cross 2.
What I will get? I will get a matrix. 2 cross 2 matrix, correct? So A1, B1, A1, B2, A2, B1, A2, B2, correct?
Yes, sir.
And what is the trace of it?
A1, B1 plus A2, B2.
Correct. Now the question is, this an inner product? So these are my vectors, and this is what the function gives: a1 b1 plus a2 b2. Is this an inner product?
No,
This
sir,
you
it
already
is
know,
not.
right?
It,
Is it? This is exactly the dot product, right?
Yes.
a1 a2 and b1 b2. If we take dot product, what we get? a1 b1 plus a2 b2, right? This is exactly the dot product of those two vectors, correct? And it is an inner product, right? If you check all the property, you will get that. And if you want me to check, suppose the first one, okay, a1 a2, so a is this. So what about trace of a transpose, right? Because this is
it
what we
will be
need.
a1 square plus
Inner product of
a2
a
square.
plus b1 square, a2 square, right? Sorry, correct? This is what we will get, and this is always positive, we know, and it is 0 only when a is 0. Both a1 and a2 are 0, correct? So first property is satisfied. Now if we check the other three will also be satisfied. I am not checking that due to time, but I request you to check it, because this is just the dot product you have seen, and I have checked inner product for the dot product, right? The dot product is an inner product. Is it clear to everyone that this is an inner product?
Yes, sir.
Any doubt in this?
No, sir. No, sir.
You have doubt? Oh. Okay, fine. Anyone has any doubt till this point? How we are checking this and all this? Right? So I think you can find this, right? Okay. The next topic was basically
Sir,
norm, right?
these all are from week 7, sir.
Yeah, but still I am seeing that these are not clear, right? If you don't want me to discuss, I am perfectly okay with it. But somehow I feel this is not clear to some of you, right?
Sir,
Because you are saying the
if you
second
can.
one as inner product, right?
It's better if you can discuss week 8 first and then come back to. If people has many doubts in that, then only you.
Okay, but you have said that this second one is inner product, no? Anyway, I am going to week 8 if you want. Okay, so week 8, everything was discussed except Gram-Schmidt. I am coming directly to.
I have some confusion in linear transform projection as a linear transformation. From there you
But
can
that is
start.
already discussed, no?
It's just one topic before the Gram-Schmidt, I think.
Okay, tell me, what is your doubt in projection?
Yes, sir.
Yeah, what is your doubt? Tell
Same
me, what
question.
is your doubt in projection?
Just you can, if you, how to take the orthonormal basis. In questions, I am getting stuck somewhere in activity questions.
Okay, so what is meant by orthonormal?
Orthonormal bases are linearly independent vectors of norm 1. Vector length is 1.
Is that enough? Only linear independence and norm 1. Is this enough?
Product of
That is
A
orthogonal
is
also.
0.
Orthogonal also, right?
Yes, sir,
Orthogonality we also need, right? Now, when we call two vector as orthogonal,
Inner product.
when the when inner product is 0.
when the inner product is 0. Great. So suppose I have a set of vector v1, v2 to vn. Okay. Suppose I am taking n vector.
Yes.
And I know that vi, vj's are 0. Mutually orthogonal, right? Mutually orthogonal means if I choose any two vector from this set where I not equal to j, right?
Yeah.
So v1, v1, this is not there. v2, v2, this is not there, like that. Right? All the other inner product will be 0. Then I will call it a orthogonal set. Orthogonal set of vectors.
Yes.
Now first, before going to projection, the first question which comes here, if I have an orthogonal set, is it linearly independent?
Yes.
Why? You are correct. It will be linearly
sir.
independent. But my question is why? We should know why. No? So this is orthogonal set of vectors. Now, why it should be linearly independent? Anyone?
Because, sir,
Orthogonal set of non-zero I should mention. Okay. Non-zero, otherwise it may not be.
yes, sir.
Because it's linearly
Yeah, now tell me why.
it's maximal linearly
Yeah,
independent set.
linearly.
Yeah, it is a set of vectors of.
I am asking why. Why it is linearly independent?
Because it's
How you check linear independence?
We
So-
check. We take the vectors and
Take the linear combination and make it zero.
yes, sir, and take the if all the coefficients are zero, then it is linear independent.
Correct. We will do the same process here. So I am taking a linear combination which is giving me zero.
Yes.
I want to show all the Ci's are zero. All C1, C2, Cn all are zero. That is what I want to show. What I will do, so if I take 0 and V1, what is this inner product?
0, sir.
0, correct?
Yes.
Because
Why?
if you include 0 in any inner product, it will become 0.
Why? That is what I have asked. Why this is 0? You have said with 7 is done, right? Why this is 0?
So you can name this equation to B, that a linear combination of all those vectors, and then you can find the inner product of B comma B1.
From the first property, we can check it, and
No, my question was, yeah, from the first property, how? My question was, I am taking 0 vector and
Yes, sir.
any other vector, right? The inner product is always 0.
yes,
Why it is true? I leave you to think about this, okay?
yes, sir.
I will come back to this. Okay, so basically you have to use the last property, okay? The last property and also some property of norm maybe. Yeah, so fine. So this is 0, that what you know already. Now here I can write 0 as the sum of this linear combination, right? I write it down because I have expressed 0 as a linear combination of these vectors. Correct? I can break it down.
Yes.
I can break it down
Also,
like
you multiplied 0 with that vector, that linear combination.
correct.
So CB comma B1 is equal to C into inner product of B comma B1. So
Correct.
C is here 0. That's why it will become 0.
Oh, you are telling me this proof, why this is 0.
Yes, sir.
Okay. Yeah, you are nearly at the same direction, but it needs a little bit refinement there.
Okay, sir.
Fine, it is fine. That is. Yeah, so getting this one, right? Cn, Vn. This one. I can take out all the scalar outside. Correct? This is what I can write down. Any doubt till this point?
No, sir.
No, right? What about these inner products? All these are 0, correct?
Yes, sir.
Because they are orthogonal.
Yes.
Except the first one, right? We don't know. So I am getting C1, V1, V1 equal to 0. This is a scalar, this is also a scalar. But we know that this cannot be 0 because I
Yes,
have
sir.
non-zero vectors, right? I have mentioned non-zero vectors. So same vector I am taking V1 and V1. This is always greater than 0. This is not 0. So C1 must be 0. Correct? Any doubt in this? Any doubt?
No,
Or
sir.
is it
No,
clear?
sir.
Is it clear to everyone?
Yes, sir.
Okay. So C1 must be 0. I can do the same argument with respect to V2. I can get C2 must be 0. I can do the same argument with respect to Vn. I will get Cn equal to 0. So I can repeat the same argument n times. I will get every Ci to be 0, which shows that V1 to Vn are linearly independent. Is it clear? That's why when we have orthogonal set of non-zero vector, we have they are linearly independent, right? Correct? Is it clear to everyone?
Yes, sir. Yes, sir. Yes.
Okay. Now, suppose I am in Rn. Will I always get an orthogonal basis? That is the second question.
No.
No? If I am inside Rn, will there exist an orthogonal basis?
Yes, sir.
Yes.
Why?
The
Why?
standard basis is always orthogonal basis.
That is
Right.
And even if I have n-dimensional vector space, if I take a set of n orthogonal vectors, they will be linear independent. And when I have n linear independent, a set which contains n linear independent vector, that will be our basis, correct? Maximal linear independent set.
Yes, sir.
Correct? And there is a process to finding that n orthogonal set that is called Gram-Schmidt, which I will come later. But for now, we know that whenever I have vector space, I have an orthogonal basis. Okay, and if I divide it with norm of each vector, I will get an orthonormal basis. What is orthonormal?
Norm of each vector
It
is
is
1.
Exactly. Norm of each
Unit.
vector is 1. Right? So if I have V1 to Vn, if I divide everything with the norm of that vector, I will get an orthonormal basis.
The unit vector
Correct?
of that vector space.
Correct. Correct. So this is what we got, right? Now what is projection? Now let's come to projection.
Sir, so every vector space will have orthonormal set basis.
Exactly. Exactly. Every vector space will have an orthonormal basis. Okay? Okay. Now, suppose what is projection? Let's find out. Suppose I am in R3. This is my x-axis, this is y-axis, this is z-axis. Right? I have a vector here. Okay? Suppose I have 2, 3, 5. So in layman's language, if I project it in on xy plane, what I will get?
230.
230, right? If I project it like this. Right? Now xy plane is what? Xy plane is basically a subspace of R3.
Yes.
Yes, sir.
Correct? It is a subspace of R3. Right? So what we are doing? We are inside a vector space V. I have a subspace W. W is a subspace of V. I am taking a vector of inside V, right? And I can project it to some vector of W. Correct? So what is projection? If I want to make it more formal, more mathematical, what should I write? Can I write this? P, I will call this projection, but P is actually a function from V to W. Right? This is what we are doing. I can do it for any vector of V, correct? Any doubt in this? P is a function
No.
from V to W.
Yes, sir.
Correct?
True.
I can do it for any vector inside V. So
Yes.
if I take vectors from W, because W is also inside V, right? What will be the projection of it?
That
Same W.
itself, same.
That itself, correct?
Yes, sir.
Yes. So basically, image of W, if I take only the W subset or W subspace inside V, that is nothing but W. P of W is basically W, right? Yeah. So this is one thing. And what about is this map onto? Is this map onto?
Yes, sir, it is onto.
Why?
Because you can project all the, your codomain set here is basically the
W.
range. Yes.
The dimension of
So basically, yeah, correct.
yes, sir. The dimension of W.
We don't have to go to dimension actually. So if you take any vector of W, I can get a P image because at least W will be a P image because W is
Yes,
inside W, no? The projection is same,
yes,
correct?
yes.
So any element inside W has a P image, and that's what onto map is, correct?
Will it
Is
always
it clear to
be?
everyone?
So this is the linear transformation, and it will always be onto.
Exactly. So projection is a linear transformation which is always on, right? This is what we get, one thing. And projection of the subspace on which we are projecting our vectors, if we take that is W, so P of W is W. These two I get, right? Another
Yes.
property of projection I have, that is called P square is same as P. And so how we can do it basically? So this is again clear from this itself. So P square means P compose P. Okay. So first I am getting my vectors V inside W. So PV, whatever PV I am getting, this is inside W, correct? If I
Yes,
have
sir.
V inside V, the projection of this vector, this PV, this is inside W. Now I am projecting this again. What I will get? I will get the same vector PV, correct? Is it clear to everyone?
Sir, can you repeat again?
Correct. So I am starting with a vector V from V. I am taking a projection PV. Now it is inside W. If I apply P again on that vector, I mean if I project this vector again in W, what I will get?
Same W.
Oh, you will
Same
get
W because this
same.
is a vector in
Yes.
W, right? So this is my
Yes.
PV. So basically P square of V is P of V. So P square equal to P, and this is true for all V. So this is the property, another property, projection. So you have seen somewhere this in assignment or activity question, practice assignment, right? So these are few
Then,
things we have to know.
sir,
Yeah,
P to the power n will also become P.
exactly. Always it will be P,
Okay.
right? If you take the higher power, it is always P. Yeah. Okay. So this is these 3-4 property which we have. This is really important for projection. Correct. So this is from the definition itself, from the just if you know what geometrically a projection is, these are, I mean, quite easy to find, right? Another question if I ask, is P 1 to 1?
No, sir, not always.
Not always, right?
Because in this case, the z-axis is actually the kernel of
Exactly.
that.
Exactly.
Yes.
Correct. Correct. Is
Sir,
it clear to everyone?
Yes,
Yeah.
yes.
Yeah.
The third property was the sir was discussing that W perpendicular is equal to V
I am
epsilon.
coming to that. I am coming to
Okay.
that.
But sir,
The
it
answer
can be
is
1-to-1 when P is from W to W, right?
exactly. It is from same vector space to same vector space.
Yes.
Correct. Exactly true. Because on W, it is basically the identity map. Correct? It is taking W
Yes,
to
sir.
W.
Yes, sir.
It is identity
Yes.
map. Correct. Till this question, anyone has any doubt? Till this point? If no, then I am going to the formal definition of projection. So what I am doing now at the beginning of today's topic, I have mentioned that inner product will help us to find projection. Right. So this is how we can find projection algorithmically. Basically, we have a subspace W of V, and now I am taking any vector V from our original vector space. Okay, and we need a subspace. So W is a subspace, and we need a basis for that. So V1 to Vn is a basis for W, the subspace itself. Right. So if I take a projection of a vector inside W, that will be a vector of W, right? That we have seen. So I should write that new vector as a combination of these VI's, right? So what I am saying, let me write here again. I have my vector space V. I have a subspace W here inside that, right? I am taking any vector here, V, inside V. I want to calculate the projection of this inside W. This is what I want to do. This W has a orthonormal basis. Any vector space has an orthonormal basis, as I have said earlier. So it is orthonormal basis of W. Okay. The projection of V inside W. So this I am specifying because I am taking projection inside W. It is a vector of W, so I should write it as a linear combination like this. Correct? If I find these CIs, what this C1 to Cn are, then I know what the projection is. Clear?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Now, again, let's go back to this place. Sorry. Now, what we generally do, how we can find this, all this. So, basically, I am taking orthogonal projection of V inside W. Right? So, what I need, V, PW, V. This is what I generally need, right? The inner product of these two, basically. Correct? And PW is a linear
Yes.
combination of this. This is a linear combination like this. Okay? So if I try to calculate this CI, what eventually I get? So you see how I have calculated this earlier. The same process I will follow here. So eventually I will get what my C1 is. C1 will be V1. C2 will be V2. Because only that portion will remain. And you know that these are orthonormal. So V2 will be 1. Right? Is it clear?
Yes.
Correct. So similarly, at the end, Cn will be Vn. That's how we find our projection. So what my projection is. So instead of C1, I have my V1 and V1. C2, I have V2. And Cn, I have Vn. Clear? So this is my projection of V on my subspace W. Is it clear to everyone?
So, sir, B is the
V is the vector I have started with. V is the vector I have started with.
okay. So here, what is B?
Right? So this is V is the vector of which I am taking the projection of.
Okay, sir.
Then the V is the vector I have started with, no? And I am taking the projection of inside W. So I can write that new vector as a linear combination of this.
Yes, sir. Yes.
Correct? C1, V1 and C2, V2, because V1 to Vn is a basis. Now my only job is to find what my CIs are. Right? Now if I find my CIs like this, then I will get my projection. Right?
Yes, sir. Okay.
Clear? Okay, great. Is it clear to everyone?
Yes, sir. It is
Is it clear to
clear.
everyone?
So, sir, for this,
Anyone has
you
any
need
doubt in
to
this?
find
They can
the
ask me.
orthonormal basis also of W, right?
Right. We have to start with an orthonormal basis. Then only we can write this linear combination. Because why we need orthonormal? Basically, when I am doing V1, at some place I have this, right? This will become my v1. Right? Now I need this one to be 1, right? Because this is orthonormal. Then only I can write this one to be 1. Correct? And all the other will be 0.
Okay, okay, sir.
Is it clear?
Yes, sir.
Yeah. So this is what basically we want. Okay. Is it clear?
Yes, sir, it is clear.
Anyone has any doubt in this? So if we don't have orthonormal, if we have only orthogonal, then basically what I will have? I will have C1 as V1 divided by V1 V1. This will only be the change. Right? Now if we have orthonormal, then this one is 1. So I will get PV1. Right? That is only the difference between orthonormal and orthogonal. Right? But we definitely need orthogonal. Other than that, we cannot. Okay?
Okay, sir.
I hope this is clear, right? So this is what projection does. Right? This is what projection basically does. Right? Now, if we check, if we want to check p square, what about the p square? It should be same as p, right? If by this, can you check that p square is actually p? Is it possible to check? P is a linear transformation, right? So if I apply PW on this, what I will get? So these are all scalars, right? So if I write this, like this. Now P is a linear map. So first we can break it down. Correct? This is the first linearity property I am using of P. Then what? This is scalar. I can take it outside. Correct? Now what are these? Can someone tell me what is PW of V1? V1 is a vector of which vector space?
W.
W. And if I take projection of that vector space, what I will get?
V1.
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 V1,
Exactly. I will get
yes.
back the same thing. So it will be again the same linear combination. Correct? So this is nothing but PWV, what I get. So yes, indeed, P square is same as P. This is really important. This property will be very useful later. Right? P square is same as P. Okay? Is this clear to everyone?
Yes, sir.
Yes.
Okay, fine. Fine. And so this is done. Now, suppose I am giving you this. So this you can try basically. So I have R3, which following represent the projection of the vector 2, 1, minus 2 onto the subspace of whole whose orthogonal basis is given. Now can we find the projection of it? It is now clear, right? How we can find it. Yeah?
Yes, yes.
So this is a vector which is given, right? 2, 1, minus 2. This is the vector which I have. And this is the orthonormal vector we have. So basically what I do, I will calculate the inner product of this U with respect to the first one. That will give me C1. Then inner product of this vector with the second one, and that will give me the second vector. Correct? So let me see how we can do this. So my U is 2, what was that? 2, 1 minus 2. Okay. 1 minus 2. This is the vector. And this vector is
1 by root 2, 0, 1 by root 2, minus 2 by 3, 1 by 3, 2 by 3. Oh, 0, 1, 0. Yeah.
0,
Sorry.
1, 0.
Yes, sir. Sir.
1, 0, 1, 0. You are saying, so this. So this is my basis of W. Is this orthonormal basis? First we have to check that, right?
Yes, sir, it is.
It is orthonormal, right? Because if you take the usual dot product, then it is giving us 0, and if you take the norm of each one, that is 1. Okay? So it is an orthonormal basis. So I want to calculate PW of U in this case. What I will get? So first I need 2, 1 minus 2. This with rest 1 by root 2, 0, 1 by root 2. This is the first inner product. And I have this vector here. Plus again 2, 1 minus 2, 0, 1, 0. I have the second vector here. So this combination, if I just calculate, I will get my inner projection. Is it clear?
Yes, sir, it's
Is
clear.
it clear to everyone? No. Right. So what is the first one? If I calculate the inner product, what I will get?
0.
Correct. So first one is basically 0.
Yes, sir.
What about the second one?
1 into 0, 1, 0.
So the projection what I am getting is basically
0, 1, 0.
on this vector itself. Okay. So if I take the projection of this in this vector space, this subspace, I am getting 0, 1, 0. Okay. Is it clear? Is it clear to everyone that how we are calculating projection?
Yes, sir. Yes.
Yes, sir.
Great. Now the next thing is, so basically you have seen that if I want to find the position of some vector, first I will need a basis of the subspace given, an orthogonal basis we need. But then I should have a process to find the orthogonal basis. Otherwise, how can I always get it? I cannot just arbitrarily choose some vector and it will be orthogonal. That is not possible every time, right? So there should be an algorithm for that. And the algorithm is basically known as Gram-Schmidt method. Okay. So what it does, what it says is basically you start with any basis that you can find, right? You have a subspace. You know what, at least one basis of it you know, right? Suppose I am giving you a subspace like this. Suppose W, I am giving you a subspace x, y, z such that x plus y minus z is 0. You can give me a basis of this, right?
Yes, sir.
What will be a basis of it?
101.
So basically z equal to x plus y. Right? So
And
you will get
0,
1, 0, 1
1.
and 0, 1. Right? So this will be a basis of W. Correct? But you can see that this is not orthogonal, right? This is not orthogonal. If you take the dot product of this is not 0. Right? So this is not an orthogonal basis. But this Gram-Schmidt method will give us the opportunity to find a basis from this basis itself, which will be orthogonal. That is what Gram-Schmidt method does. So what it does basically, so the process is pretty simple here. So keep the first vector as it is. We are not changing it. Keep the first vector W1 as V1. What I will do, I need orthonormal, right? Eventually I need orthonormal. So we can start from there itself. I can divide it with this norm. The first vector, I am naming it as W1. I am dividing it with its norm. That will give me a unit vector. So for the first vector, I really don't have to bother so much. I just want to make it as a unit vector. That I have done. Now, what about the second vector? How will we construct the second vector? This is where it comes interesting. Right? So you see how it is done. Right? let me explain this, why this process is working. So V1, V2, Vn. First step is what? I am taking this vector, I am naming it as W1, and I will call my new vector U1 as W1 by norm of W1. So this is a unit vector. So I want to find some vector here. So first vector is U1. This is a unit vector I am getting from here. Right? Now what about the second vector U2? How I can get it? So first construct W2. What is W2? Here it is written like this. So first let me write down what it is. So U1, V1, V2. Right? See, this is what I am getting here. V2, U1 with respect to E1. Now what this is? Sorry, this is V2. Now what this vector is? Why we are constructing this vector? Any idea why we are doing this? Why we are doing this? Basically, what was our goal? I need some vector which is orthogonal to it, right? Which is orthogonal to it. So if we take orthogonal, I mean inner product of these two, what eventually I will get? This is right, and what I will get from here? Am I getting 0 from here? Can you hear me what I am saying?
Yes, sir.
So what I need to do here? What is this inner product? That is what I am asking. What is the inner product of W1 and
V1, V2
V1, V2
minus
this
V2 U1 is a scalar that can be taken out
exactly
into V1, V1.
Correct. This is what I am getting, right?
Yes, sir.
Now, suppose if this V1 is of norm 1, okay, eventually I will get like this. The C1 will be norm 1. So if this was in norm 1, so this will be 1, right? So this is the same vector, right? V1, E1, V1, V2. I have written it wrongly somehow. V1. Why I am writing V1 here? U1. This is U1.
Yes, sir. U1 is 1, sir.
So this is also U1. This is what I am getting U1, V2, and here I am getting U1, U1. So this is 1, and these two are exactly same vector due to symmetricity, same scalar, right? V2, U1 and U1, V2. So this will cancel out. So this will give me 0. So that is what we wanted, right? Yeah. And what is this one? If you remember, what is this one? I have already U1 as my vector, right? So if I take a subspace which is span of U1, and I am projecting my vector V2 into that, this is what I will get, right? Are you getting what I am saying? I am.
Sir, W1 is V1, no, sir. So the
W1
first
is V1. Right.
So in the first place, we need to write V1, no, sir.
No, I have created U1, which is basically dividing with its norm.
Yes, sir.
Right. So I am getting my new vector U1, which is basically the V1 divided by its norm.
Yes, sir.
Like that.
Means unit.
So that is what I call U1.
Oh.
Right.
Okay. Okay, sir.
And then I have U1. So I have a subspace like this. Correct? This is a subspace. This is my new, say, W, my subspace. Right? Now I have vector V2, which is outside this span, right? Which is not in the span, because I have started with a linear independent set. This set was linear independent because this was the basis, right? Basis of RL. So this is linear independent. So V2 is not inside span of U1. Is it clear to everyone? Now, what is the projection of V2 inside W? Just now we have calculated. How we calculate the projection? This one. Because U1 is itself an orthonormal basis of W. Correct?
Yes, sir.
This is the projection, right? This is the projection I am getting. Right? Is it clear to everyone? Or should I explain it from the beginning again?
Sir, can you just expand and show how it is projection? I'm not able to get it.
Right. So let's come back here again at this point. If I start with a vector V and I am taking a projection inside W, what I generally do? I take a orthonormal basis of W and the projection of V inside W will be this combination, which eventually will give us VVI, this inner product, VI, right? 1 to n. This is how projections work, right? We have checked it already. Now let's come back here. Let me start from the beginning. I have started with this set. So this is linear independent, that we know. We have started with a linear independent set. What I do, basically, I want to find a set which will be orthogonal set, orthonormal set eventually. So first, let's call it W1. V1 I am calling it W1, and I am dividing it with this norm. So this is an unit vector. This is a unit vector. I am writing it here. Right? Now I am considering span of U1. Okay. I want to find some vector from V2 which will be orthogonal to it.
So why you are taking, sir, V1 is equal to W1?
Write the algorithm properly. So basically, if you just do V1, non-V1, that is your U1. That is what you are saying,
Yes,
right?
yes.
Why I have inserted another W1, I will explain it later. Okay.
Okay.
I am coming to that. For now, this is same. There is no point of writing W1 for now. But why I have written it, I will come back later. Okay. Then what I am doing, I am considering a subspace of our original vector space of span of U1. So this is a subspace W. So U1 is an orthonormal basis of W, right? Because only one vector is there and which is normal. Unit vector. So it is an orthonormal basis. Correct? Now if I want to take projection of V2 inside W, what I will get? How I will get? I will do V2 U1 U1. This is the projection.
Yes, sir.
Correct? Is this clear to everyone?
Yes, sir.
Okay. Now I got this projection vector. Right? Now if I do this vector is basically orthogonal to U1. This vector is basically orthogonal to U1. So what it looked like basically, I have taken a projection. Suppose I have U1 here. So a vector, and this is the subspace generated by it. I have another vector here. I have taken a projection like this somewhere here. Right? This is my vector V2. There is some vector U1. This is the span of it. I have taken a projection of it. So this is PWV2. Right? So if I subtract V2 minus PWV2, what I get is basically that is orthogonal to U1. Is it clear?
So, sir, how you got the subtraction of that B2 minus?
Just subtraction of two vector. You know addition, right? So this is just vector addition. Take projection vector, take the inverse of it, add these two vector. Right? The usual subtraction. I mean, this is nothing new, right?
So the two lines are perpendicular, sir.
Exactly, and this basically gives the perpendicular thing. This subtraction represents that thing. Correct? So this is my new vector W2. So we only get till perpendicular thing, the orthogonal thing. So my point is W2 U1. This is 0. Right? And is it clear to everyone? W2 U2 is 0. We have already checked it. So W2 is this one, U1. Right? And if I expand it, now this is V2 U1, keep it like that. Projection, we know what is the projection of V2 on U1, span of U1. So this is V2 U1, U1. And this is U1. This is what we get. This is a scalar. I can take it outside. U1, U1. This is orthonormal, I know. I mean, unit vector. So U1, U1 is 1. So V2, U1 minus V2, U1. This is 0. So indeed, this is orthonormal to it. Is it clear? This vector? That this vector, the new vector W, is basically orthogonal to U1. Right? Now, if we divide W1 by its norm, W2 by its norm, I call it U2. Now, if I consider U1, U2, that will be an orthonormal set, right? Which we got from V1 and V2. Is it clear? Is this question clear to everyone?
Yes, sir.
Imagine this a little. So this is what we are doing here, right? We start with V1, V2, Vn. First call this V1 as W1. I am dividing it with its norm. I am getting U1. Now I am considering the subspace span by that. Now when I am considering the subspace span of U1, we know that V1 is not inside that. V1 is outside that. Correct? Because that was linear independent. So V1, V2 is not inside W. That we know. Because it was linearly independent. So it cannot be inside the span of U1. What we will do, we will take the projection of V2 inside the subspace W. I am taking the projection, and that's how projection is. Now, V2 minus the projection is basically perpendicular to U1. That is what we get. And we have checked it also. This is orthogonal. Right? So we get some vector W2, which is V2 minus projection of V2 inside W. That is my new vector W2. We are dividing W2 with its norm. I am getting U2. That is my second vector in the set. So U1 and U2 both are unit vector and they are orthogonal to each other. Is it clear? Is it clear to everyone?
Yes, sir.
Yes, sir.
Great. Next step, again, same thing I am repeating now. So from V1, V2 to Vn, till now I have got two vectors, U1 and U2, which are perpendicular to each other, basically orthogonal to each other, and they are unit vector. What about the third vector? Now I have to consider the third vector. Same process we will do. I will first consider a new subspace W prime, which is span of, now which vector space I should take? U1, U2. Now I have my new vector space, two-dimensional vector space. This V3 will be outside that because V3 was linear independent, right? These all vectors, this set is linear independent. So V3 cannot be within the span of U1 and U2. We take the projection of V3 inside W prime. This is the projection, right? If I take V3 minus projection of V3, we call this as new vector W3, right? And what was projection of V3? V3 U1 plus V3
U2, U2.
U. This was the projection, correct? Now let's check what we need. We need W3 U1, this should be 0, and W3 U2, this also should be 0. Is it happening or not? That is what we need to check, right? So what is W3 U1? So W3 is V3 minus projection of this with U1. Let's see whether this is 0 or not. This is V3 U1 minus V3 U1. V3 U1 minus, what is projection of this one? This is V3 U1 plus V3 U2 comma U1. V3 U1 minus, we can break it down and take the scalar out. I am getting this. So last thing I should write clearly little bit. V3 U2. This is U2 U1. Now tell me what is happening here. What about this one? This is 0, right? Because U1 and U2 was orthogonal. We have already seen that. So this is 0. U1 was a unit vector. So U1 is 1. So this is 0. So indeed W3 U1 is 0. Similarly, if we calculate W3 U2, that is also 0. W3 U2, if we calculate, that is also 0. So we get another vector W3, which is orthogonal to both of these, because that's how we have constructed it, right? We take the span of U1 and U2, I will get something like this plane. V3 is outside that, take projection vector here, right? So this is basically span of U1 and U2. This is my V3. So here is projection. I take this V3 minus projection vector, then it is perpendicular to the span, right? Perpendicular to the space, vector space which is below. And if I write U3 as by W3 by norm of W3, I will get a orthonormal vector with respect to U1 and U2. That's how we can move forward until at the end we will come to UN, right? So I am getting a orthonormal set, orthonormal basis from a given basis. Is it clear? Is it clear how Gram-Schmidt works?
So show some examples.
But at least the process is clear. What we should do?
Yes, sir.
So, yeah. So now let's come back to why you have asked that why I have given the name W1, right? So first, I am starting with this linear independent set. Okay, a linear independent set I am starting with. I'm calling it V1. I am defining U1 as V1 divided by norm, sorry, W1 divided by norm W1. This is my U1. What is W2? W2 is basically V2 minus projection of inside this span. So I write directly the formula V2 U1 U1. So this is my W2, the new vector, and U2 is basically I am taking the unit vector with respect to that. What is W3? Taking V3 from here, V3 U1 U1 V3 U2 U2. This is my W3, and what is my U3? W3 by norm of W3. So if I write it algorithmically, what is Wi? Wi is take Vi minus all this, right? Vi U1 minus till Vi I minus 1. I minus 1. This is my Wi. And what is my Ui? Ui is Wi by norm of Wi. So if you want to write a programming with respect to that, you have to define both Wi and Ui separately, right? So first step, if although we have V1 as same as W1, but we have to name it as W1. If we have to write in algorithmically language, otherwise this is the same. But as you have seen, for the letter we need W1, later we need W2, W3, so on. So in the first step also I am naming it as W1, then dividing it with this norm. Is it clear? Is it clear what I am saying? Anyone has any doubt in this?
No.
Is it clear
No,
to
sir.
everyone? Okay, great. So suppose I have given a vector like this 1, 2, 2 minus 1, 0, 2, 0, 0, 1. Okay. 1, 2, 2. What was next? Minus 1, 0, 2. And next one is 0, 0, 1. Okay. This one. So from this one I have to find an orthogonal or orthonormal basis. So this is my V1, this is my V2, this is my V3. What my W1 should be?
1, 2, 2.
1, 2, 2. What is my U1?
W1 by norm W1.
What is that? What is norm of W1?
3.
3.
3, sir.
So
Yeah.
1 by 3.
2 by 3, 2 by 3. Okay, 1
I
by
am
3, 1
writing
2.
like this.
Yes, sir. Yes, sir.
Okay. Now what is W2? W2 is basically V2 minus
V2 U1, U1.
U1. So what is my V2? Minus 1, 0, 2. So this is the projection of V2 in span of U1. So minus 102. U1 means 1 by 3, 2 by 3, 2 by 3. And 1 by 3, 2 by 3, 2 by 3. This is what it is, right? What is the inner product of this first two? 4 by 3 minus 1 by 3.
1, 3 by 3.
1.
1. So it is 1, right? 1 by 3, 2 by 3, 2 by 3. And if I do this subtraction, what I am getting?
Minus 4 by 3. Minus 2 by 3. 4 by 3. Plus 4 by 3.
2
minus 2 by 3, sir.
4 by 3.
6 minus 2. Yeah, plus 4 by 3.
4 by 3. So this is my W2. Now what is U2? W2 by norm W2.
Yes, sir.
So you have to calculate the norm. What it is? 16 by 9, 4 by 9.
16 by 9.
What is that?
36 by 9.
6 by 9, 4. So 2.
It's 2. 2, sir.
So half. Okay. So this is my U2. Correct? Now what about the last one?
Can we cancel that 2, sir?
Yeah, we can actually. So it is
Minus
minus
2 by 3. Minus 1 by 3.
1 by 3.
2 by 3. Yes, sir.
Correct. Now what about W3? It is V3 minus V3 U1 minus V3 U2 U2. Correct? What was V3? V3 was 001. It is quite good looking V3. So 001 U1. What was U1? 1 by 3,
2 by
2 by
3,
3, 2
1,
by 3.
2 by 3.
Right? It was 1 by 3, 2 by 3, 2 by 3. Huh. Right. So this is 1 by 3, 2 by 3, 2 by 3. Minus again 001. U2. U2 is minus 2 by 3.
Minus 1 by
Minus
3,
1 by 3, 2
2
by
by
3.
3.
And U2 is
Minus 2 by
minus 2
3.
by 3, minus 1 by 3, 2 by 3. Correct?
Yes, sir.
Yeah. So this is 001. What about this one? The inner product? This is
2 by 3.
2 by 3. 2 by 3, 2 by 3. And this one again 2 by 3, right?
Yes, sir.
Minus 2 by 3, minus 1 by 3, 2 by 3. So basically we have to do this calculation again. 2 by 9, 4 by 9, 4 by 9. So let me do minus 4 by 9 minus 2 by 9, 4 by 9. So minus 2 by 9 plus 4 by 9 minus 4 by 9 plus 2 by 9, 1 minus 4 by 9 minus 4 by 9. This is what it is, right? So 2 by 9 minus 2 by 9. And what is this? 1 minus 8 by 9. 1 by 9. Right? So this is your W3. And U3 will be W3 by norm of W3. So whatever you get from here, that will be your, what is the norm? 4 by 81 plus 4 by 81 plus 1 by 81. So 9 by 81, right? So 1 by 9, 1 by 3. So it is 1 by 3, 3 into W2. 2 by 9 minus 2 by 9, 1 by 9. So what it is? 2 by 3 minus 2 by 3, 1 by 3. Okay, so you get U1, U2 and U3, and that is your orthogonal set of vectors corresponding to V1, V2, V3. Is it clear? So this is basically the algorithm is. If you know the algorithm, you can directly find it.
Sir,
Right?
I have a
Sir,
question.
once show me the answer, sir.
One by one. Go ahead.
Please show me the answer, sir, once.
Yeah. And what is your question? Someone else was asking me.
Sir, in this
Yes,
method,
sir.
sir, if in this method we take V1 is equal to the third vector, that is 0, 0, 1, and if we implement this algorithm, then will there be any change in the answer, or it will be correct? It will also be correct. Because
V1 is
now if it see the third vector, that is 0, 0, 1, which is already a
right.
unit vector, so we did not
Right.
divide it by the norm, so
Right.
that it will make calculations easier. So if we take it that way, will that answer be also correct?
No, that will be different. No, because ordering is important for a basis. No,
Okay.
because you know the matrix representation depends on ordering. So order of a
Yes.
basis is really important. So
Okay.
you should maintain the order, right?
Okay. Thank you.
So did the session start at 7?
No, 6. Why?
Sir, I didn't know that.
Oh. Yeah. So this is so Gram-Schmidt is clear to everyone. Any doubt in Gram-Schmidt method? This is nothing very difficult to see. Gram-Schmidt method, right? Anyone has any doubt till this point?
No, sir.
Projection and Gram-Schmidt method? No doubt? Okay, great. Yeah. So now the last section is basically orthogonal transformation. So now we have a vector space with an inner product, right? So which we'll call inner product space. So vector space with an inner product. Now suppose we have a linear transformation from the vector space to itself. T is V to V, like R3 to R3 or R2 to R2. And in both the side we have some inner product, right? It may be the usual dot product or it may not be. It is some inner product which is given, right? And now if that linear transformation respect the inner product, then we call it an orthogonal transformation. What does it mean? So let me.
Hello, sir. In lecture, sir said that this lecture 5 is not important for data science. Then question asked in the quiz for this
Yeah,
question.
there will be question from here.
Okay.
So V to V. Okay, both are inner product. So here I have some inner product, right? In this side, say call inner product 1, and here I have some other inner product, maybe, or maybe they are same inner product, right? So as we are considering V as the same, so here when I am writing V, the same inner product space, then inner product are also the same. So this is the first thing, because here if you see the definition, V is an inner product space. That means in the both side of V we have the same inner product, not different inner product, right? So suppose I have here two vector V and W. So I will get an inner product with respect to this, right? That will give me some scalar. Now I have the images. So this is my V, this is my another V, another copy of V. I have V and W. This is V, this is W. This is going to T of V. This is going to T of W. Right? We calculate the inner product V, W here. That is giving me some real number. Here also we can calculate TV and W, TW with respect to the same inner product because we are inside V. If these two give me the same real number, the same scalar, if these two give me the same scalar, TV and TW, the same as V and W, then we call it an orthogonal linear transformation. Clear? Is it clear? So suppose and there is something called orthogonal matrix. So if you remember, so what is orthogonal matrix? If we take the matrix and take the transpose of it, it will give me identity matrix. If it happens like that, then we call it an orthogonal matrix, and it should be from the both direction, A and AAT, both the. So basically we need a square matrix for that, otherwise the product will not be defined. So what I am saying, A and AT should be same as ATA, which is giving me identity. Then it is called orthogonal matrix. And as the name already suggests, so there must be a relation between these two, right? And what is that relation? That is basically why we call it orthogonal linear transformation. So inside a finite dimensional vector space, that means R2, R3, or Rn, this type of vector spaces, or all those vector or matrix spaces, which are finite dimensional. So we generally work with finite dimensional in this course. The matrix representation of orthogonal transformation with respect to orthonormal basis is an orthogonal matrix. So here it is really important that we have to write the matrix representation with respect to the orthonormal basis. Otherwise, it may not be orthogonal matrix. Okay. So we have an orthogonal linear transformation. T is orthogonal. Okay. Now, if I have any basis beta, which is not orthonormal, then the matrix differential with respect to this may not be orthogonal matrix. This is really important. It will be orthogonal, or it must be orthogonal if your beta, the basis you are taking, it is orthonormal. Only then T beta prime is orthogonal matrix. Okay. So this is what the definitions are, and you know that rows are mutually orthogonal vectors with unit norm. That is quite clear, right? If you take the rows of the matrix, because here, suppose let's take a 2 cross 2 matrix, A, B, C, D. Okay, and if I take it transpose, what I am getting? A, C, B, D. Right? So what I am getting here is A square plus B square. What I am getting is AC plus BD. Here AC plus BD and C square plus D square. This is identity matrix if this A is orthogonal. Right? If A is orthogonal matrix, then this is 1, this is 0, this is 0, this is 1. So what I get A square plus B square as 1, AC plus BD as 0, and C square plus D square also 1. So if I consider this row vector AB and CD, these are my row vectors, right, of the matrix A. Correct? What can I talk about this? If you see the inner product of usual dot product, if you see, what is this? This is AC plus BD.
0.
Correct? And this is 0. So they are orthogonal, right? They are orthogonal. And what is the norm of this one? This. And this is 1, right? Because we have this. Right? So norm basically square of it. So this is 1. And similarly for this one, the norm is 1. C square plus D square is 1. Right? So norm of this is 1. Norm of this second 1. So this is orthogonal plus each of these are a unit vector. So eventually these become orthonormal. Clear? So the row vectors of orthogonal matrix is basically forms an orthonormal basis for the row space. Is it clear? Is this statement clear?
Yes, sir.
Sir, please repeat once, sir. The last statement.
The statement is I am saying the
Row vectors
of the matrix will form a basis, orthonormal basis for the row space.
Of orthogonal matrix.
Of orthogonal matrix. Correct.
Yes, sir.
So
Yes,
I have started with an orthogonal matrix A.
Mm.
A is my orthogonal.
Yes, sir.
The rows of A,
Mm.
AB and
CD.
CD. These are rows, right? 2 rows.
Yes, sir.
This will be an orthonormal basis for the row space. Row space means span of the row, right? That
Yes,
is
sir.
called row space.
Yes, sir.
And this will form an orthonormal basis for it.
Yes, sir.
That is one important property of orthogonal matrix. Clear?
Yes, sir. Thank you, sir.
That is what we have checked here.
Sir, this orthogonal matrix is different from the orthonormal set, sir. Orthogonal set.
What is orthogonal set?
Inner product of Vi, comma Vj is 0.
Those are defined on some vector elements, right? Vectors. And this is called matrix. Right? I am taking A as a matrix. Correct? So a matrix is called orthogonal matrix if A A transpose is same as identity. So this property A transpose is same as A transpose A, and this will be same as identity. If this happens for a matrix, then we call it an orthogonal matrix. Now what I am saying, if you take out the rows of the matrix like A, B, C, D, these are two rows. This row will form a orthonormal basis for the row space of the matrix. Clear?
Yes, sir.
Is it clear? Okay, fine. Okay, so now the last statement may be here.
Sir, one
The
question.
columns.
Sir,
Yeah, yeah.
see, suppose they're given a linear transformation that then asking us to check whether it's orthogonal transformation or not. So how do we check that?
This condition. This condition you have to check.
Can you just give me some examples?
Okay. In activity question, do you have any?
Yeah, we can solve with us.
Solve with us.
Question number 8, I think.
Take that. Solve with us. Question number 8, is it? Okay. Correct. This one, right? Right. Now suppose you take T1 and T2, say which one? Say second one, okay? X plus 3y, 2x minus 2y. This is how it is defined. Can someone repeat what is the second one? Txy is? X plus 3y, 2x minus 2y. X minus 2y. Okay. So what I have to do? Take P as x1, y1 and W as x2, y2. Correct? So what we have to check? We have to check VW. The inner product is same as TV, TW. This is what we have to check, whether it is satisfying or not. Now what is, first check TV, TW, right? So what is TV? TV is x1 plus 3y1, 2x1 minus 2y1. And what is TW? x2 plus 3y2, x2 minus, sorry, 2x2 minus 3y2.
2y2.
Correct. Now if I take TV, TW, this is nothing but the dot product, right? With respect to usual one, we are checking. So what I am getting?
x1 plus 3y1 into x2 plus 3y2 plus 2x1 minus 2y1 into 2x2 minus 2y2.
Correct. If I simplify this thing, do I get anything special?
Sir, I think they will reduce to some low form.
It will come something? What you are saying?
We can go
Means
for x1, we can add
reduce
x1,
it
x2
from
terms.
shortest
Simplify that.
form, and then we can match it with V and W.
That is what we are going to do basically. Correct. So 4x1 y2 plus 4y1 y2. Now see what cancels up, and what is VW? VW is x1 x2 plus y1 y2, right? So is it coming simply after simplification? Is it coming like this? That is what you have to check, right? Okay. So if this matches, then it will be orthogonal. If it does not match, then it is not. Is it clear?
Yes, sir.
But by seeing the
But it is
can we say something like this?
Huh?
By seeing the dimension of the, can we decide anything?
No. Directly we cannot.
Okay.
Directly we cannot. Yeah.
Sir, are there any short tricks, for determining this transformation at inner product? Any
Without using inner product.
no, we are using inner product, but any short trick just for to MCQ, just for approach of MCQ questions.
No, basically you have to check it. This definition you have to check it. Otherwise, there is no way.
Okay.
Right?
Means from this definition, any sub thing or subtopic follows, and from there we can quickly check. Is there something like that?
No, directly I insist you to check this one.
Okay.
Right?
Will it be on to or one to one? Is there anything can be said about this, sir?
Even if it is, but all onto map is not orthogonal, no?
Okay.
I mean, the property you are mentioning, I know, because there are some property, but that is all one directional. If that happens, that it may not be orthogonal always. If it is orthogonal, then something happened. This is true. Because if you see this, what I have mentioned here, so if the matrix representation of orthogonal is an orthogonal matrix, then but it is not the converse direction. You directly don't know the given transformation is orthogonal or not. It is saying if it is orthogonal, then the matrix representation with respect to it is an orthogonal matrix. But we don't know about the converse direction. That is the issue.
Okay.
Got it, no?
Okay.
We have to check it. And similarly, so what I was suggesting earlier, that if we have an orthogonal matrix, if we take the row vectors, that will form a orthogonal basis for the row space. And similarly, column will also do, because we have A is identity. If we use this identity, then we will get the column vector will also do the same thing. Okay. Now, suppose if we have this property. Okay, so I have linear transformation like this. I have two bases like this. Okay? This is standard order basis, but first one is standard order basis, the second one is not, ordering is not the same. Right? Now the question is whether, so suppose you see option 3, T is orthogonal linear transformation with respect to dot product. Now if you have to find it, you have to go through that process. Right? You have to check whether it is forming an orthogonal linear transformation or not. Right? And it
Sir,
is not, as you can see, yeah. Yeah, tell me.
No, sir, you continue. I will ask afterward.
So here, here my point is, here it is not very difficult to check, right? As the linear transformation is defined. Correct? So what you have to check here? So the problem is like this: x1, x2, x3. It is going to x2, x3, x1. I think that is it is given. No? x2, x3, x1. Correct.
Excuse me, sir.
Yeah.
Sir, we have start session at 8 p.m.
Yeah, those who want to. I will finish by 2 minutes.
Anything else left, sir? This is the last one.
This is the last topic of week 8.
Okay.
So,
thank you, sir.
Yeah. So here, if we want to check the orthogonal, whether this transformation is orthogonal or not, what we have to check? We have to check two vectors, right? Again, x1, x2, x3, and w as y1, y2, y3.
Sir, your voice is not.
My voice is not coming.
Now it is clear.
Okay. So what is VW? This is x1, y1, x2, y2, and x3, y3, right? With usual dot product. And what is TV, TW? So TV is basically x2, x3, x1, and TW is basically y2, y3, y1, right? The inner product of this. And as you can see, this is same thing. Right? We are getting the same thing. So T is indeed an orthogonal linear transformation. Now, if I just ask if it forms the matrix representation of it with respect to standard ordered basis, will that be an orthogonal matrix or not? Can you tell me directly?
Yes, sir, it is.
It is, right? So if I write the matrix representation with respect to T beta, right, then it is an orthogonal matrix. That is what.
In both the cases, it would give orthogonal, right?
Right, both the cases it will
Because
be orthogonal. Exactly.
because the order is only different. Both are standard order
Exactly.
base.
Correct. So both of those bases are basically an orthonormal basis. So if you take the matrix representation with respect to both will be orthogonal matrix. But here you can check that. I mean, is T 1 to 1 or on to anything you can say about this? What about 1 to 1 on to this?
Sir, I am unable to derive option 1 as well. How to do it?
So option 1 is saying that there exists some n for which T power n is identity, right? Where identity is inner. So basically, there exists some n. So what it does, T x1, x2, x3 is x2, x3, x1. This is what I have. If I apply T1 once more with this T, so this is T square. What I am getting, if I apply T on this, can you tell me?
I think this x3 will come first. X1.
X3, X1, X2.
Yeah.
Exactly. If I apply T once more, which is T cube, so T of this, what I will get?
X1.
Same.
X1, X2, X3, right?
Equal to T.
So what I am getting? I am getting T cube of X1, X2, X3 is X1, X2, X3. Right? So T cube is basically identity mapping. So there exists some n for which T power n is identity. That is what the first option was.
Okay, sir.
Got it, no?
Yes, sir. Now got it.
Now
Actually,
if we apply T1 more, then T4 is basically T.
Yes, sir.
That
It
is
is
the second
equal
option.
then.
Got it?
Yes.
So this is basically what we have. Is it clear to everyone?
And for 1
So
1.
this is more or less what we had in, yeah.
And for 1 and 1 on 2, that is.
That is easy to check. This is the given, right? Transformation. What is the kernel of it? What is the kernel of T?
0, 0, comma 0.
0,
right. So if it goes to 0, 0, 0, then x1, x2, x3 all must be 0, right? So kernel is nothing but the 0 vector.
Okay.
This. So kernel is 0 vector means what? Is
1 1.
1 to 1. Correct. And kernel is 0 means nullity is what? Nullity is 0.
Yes.
Nullity of T. Then what about the rank?
3.
3. And rank 3 means here, what is? This is 1 to 1. Right. T is from R to 3 to R to 3.
Yes.
Right. So the rank of the dimension of the codomain is same as the rank. That means T is 1 to 3.
Okay.
Yeah. So it is both 1 1 and 1 2. So it is an isomorphism. So it is an isomorphism. It is a orthogonal linear transformation. All this we have in this problem. Okay. Clear?
So nullity is dimension of kernel, sir.
Right.
What exactly is rank, sir?
Rank is dimension of the range.
Okay, sir.
Rank is dimension of the range, right? Dimension of the image space. Okay.
Sir, one question.
Yeah.
There was a basis given, no, sir? Beta and bar. What is the use of that basis?
No, that was for the next problem. There are two questions. Answer the following question.
Oh, okay.
So there is the next question.
Okay.
Which will. So basically, what I was saying. So if we express the matrix representation of T with respect to beta, right? That will be an orthogonal matrix, right? Because this is an orthonormal basis, right? So if you express this, then you will get some matrix like this. So you can conclude that option 1 is correct. So that will give you the idea. You don't have to check the matrix multiplication here for orthogonality. You can check. I mean, you can write AAT, but you really don't have to check that. Okay? Is it clear?
Yes.
So we should only check whether the rows are orthogonal.
That is also you can check. That is also you can check. Now you know many similar condition, right? So here what I have written. You can check any one of these. That is enough. Okay? But for finding a transformation is orthogonal or not, I think it always better to check from the definition. Check the inner product. Right? There are some special cases where some property may be used, but in general, this is the definition, so it is better to check by this definition. Okay?
Sir,
yeah.
Can I ask any doubt now?
Yeah, go ahead. So basically, I don't have anything to say on week 8.
Sir, can
Those
you
who want to leave?
that week 7 which problems you will discuss?
Week 7?
Sir, I actually have from week 8 only from practice assignment. So I just
Okay.
wanted to clear it first because week 7 it is like gone by, and then it would be useful for everyone. Week 7 is also
Which one?
Second question.
This one?
Yes, sir. This I am not able to formulate that general. I'm not able to decode that general problem, that which is true or which is false.
This is I have discussed today.
Today?
Yeah.
Okay, sir. So I will watch it.
Can you point it out? So statement Q I have proved already here. Right.
Okay.
So I have started with the definition of projection. So projection, I can talk it as a linear transformation from the vector space to the subspace to which we are projecting. Right. Then it has some property, and that I have discussed today. So if you can see, and then if you can go back to this problem, I think that will be easier.
Okay, sir. I will do it.
Yeah. Fine.
And sir, this circle means multiplication or composition?
Composition.
Means
this is composition.
What? That function thing, t of t.
Composition of two functions.
Okay, sir. Thank you.
Yeah.
Sir.
Yeah.
Sir, can you please give some hint to solve graded assignment question number 9?
Graded assignment is still due, no?
Sir, but only some hint. I tried, but I not getting it. Question number 9.
This is just finding the projection, the nearest distance in finding the projection.
This, sir, x plus y plus z plane, how to, for all the
that
other...
is a subspace, right?
Yes, that is
x plus y plus z, that is a subspace, right?
Yes, sir.
So you can find a basis for this?
Yes, sir.
From that basis, using Gram-Schmidt, can you find an orthonormal basis for this?
Yes, sir.
If you have an orthonormal basis and if you have some vector, can you calculate the projection of it?
Yes, sir. Yes, sir.
Then it is done.
Okay, sir. Got it.
Okay. Yeah. Amruta, you are saying something about week 7, is it?
No, sir. At the beginning, you were discussing some problems in the slides.
So basically, I was discussing the basic stuff of inner product and norm. So one thing I have mentioned why bilinearity is important. That is what I have already discussed. And another thing which I had in mind was all the norm may not come from inner product. Is it clear to everyone that all the norm may not come from inner product?
Means, okay. Can you explain?
So you know one norm, right? Uh, Norm has some property, right? That you know. Correct. Now, if I have this norm of x, so I can define it like this. Correct? So there is a definition of norm which takes inner product into the account. So this norm is defined using inner product, right? But there may be some norm which does not use inner product in its definition. That is what I tried to say. So if you consider this, suppose, so this norm you know, right? This is a norm. This part is clear to everyone, is it?
So this is standard, no? Standard.
This is standard. This norm is basically what we get from inner product. So if we have an inner product space, we have a norm. But suppose we don't have any inner product, still we can have a norm, right? Still we can have an idea of the length of a vector. How? Suppose I have in Rn, I am giving you an example in Rn. Okay, suppose I have vector x or vector v, I should write v. This all should be v. Okay, so I have vector v, which is like x1 to xn. Right? This is a vector in Rn. Now I can define a norm like this, which is maximum of mod of xn. So can you check? And this is called max norm. So how it works? Basically, suppose I have a vector like this 2, 3, 0, 1, 9 inside R5. Okay. What is the norm of it?
9.
According to this 9.
According to this 9. But according to this
Yeah.
norm, it will be something different. But can you check that this satisfy all the property of norm? That is what remains, right? So if you check all the property, this will give you the norm. So what are the properties of norm? So if I go back here, yeah, these three properties you have to check, correct? The triangle inequality, the scalar thing which comes up, and the positivity. It is always greater than equal to 0 unless it's 0. So these three you have to check. And if you verify this, then it will be satisfied. Why? Because suppose you have this x1 to xn and say v, this is v1 and v2, say y1 to yn. So norm of v1 is maximum of xi and norm of v2 is maximum of yi, mod of yi. And what is v1 plus v2? x1 plus y1 till xn plus yn. So what is norm of v1 plus v2? Maximum of?
Maximum of xi plus maximum.
No, maximum of xi plus yi. So now these are the coordinates, right? So of which one is maximum, we will take that one. Now this triangle inequality hold for each one, right? You know this one. This is always true for mod, right? The triangle inequality. So eventually for maximum also this is true. Okay? So we get the inequality we need. Norm of v1 plus v2 less than equal to norm v plus norm v1 plus norm v2. Right? So first property will hold. Similarly, if you take the second one, the scalar. So suppose I have this one, say b as x1 to xn.
Sir, I didn't get this max of xi plus yi mod that is always less than max of x.
Because mod of xi plus yi, this is always less than mod of xi plus mod of yi, right?
How, sir? That's a.
This is the just triangle inequality of modulus. No?
Okay.
This is just triangle inequality. So basically, if we have what I would say, This is the basic Pythagorean triangular imperative of numbers. If you have two real number, right? Two real number, A and B. Correct? If you take mod and add this, or if you add this, A plus B, take the mod, that will be always less than mod A plus mod B.
Okay.
Right? Suppose you have -2 and 3. Okay. So what is mod A? Mod A is, suppose this is your A, this is your B. Mod A is 2. Mod B is 3. And what is A plus B? 1.
Yeah.
Mod of A plus B? 1.
Okay.
That is always less than 5.
Okay.
So whatever number you take, it will always...
Okay, less than or equal to. Okay.
Because mod works like that.
Okay, got
Because
it.
mod will take to the positive side. Right?
Got
If
it.
you add this, even it goes to the negative side, if you take mod, it will get back to the positive side. So eventually we'll get it, this inequality.
Yeah, got it, sir. Thank you.
Okay, yeah. Okay, fine. Now, what about CV? CV is basically Cx1 to Cxn. Right? So if you take norm of V, what is this? Maximum of mod of xi for some I. And what is norm of CV? This is maximum of mod Cxi. Now this C, I can take this, I can write as maximum of mod C into mod xi. Now this C can come outside because it is scalar with respect to everyone. So it will come out. So we will get norm of CV same as C, mod C into norm B. Correct? That's why this mod is important here. In the definition, that's why the mod is important. If we don't take mod, it will not work. So similarly, the last one. So it is maximum of all the mods, right? So mod can never be negative. So it is always greater than 0. And whatever the maximum is, it must be greater than equal to 0. Now when it will be 0? It will be 0 when maximum is 0. So maximum is 0 means what? All the mod must be 0. And when all the mod are 0, when all the xi's are 0, so all this xi's will be 0. So V1 is basically a 0 vector. Is it clear?
Yes.
No. Because basically when norm of V1 will be 0. That is my question. So if norm of V1 is 0, that means maximum of this mod of each coordinate, that is 0. Now maximum is 0 means what? Everything is 0 because they are all positive number. So all this mod of xi's are 0. Now when all this mod of xi's are 0, when all the xi's are 0, so all this coordinate will be 0. So V1 will be 0. And only when 0 is possible. Otherwise, it is always greater than equal to 0. Okay? So it satisfies all the definition of norm. And this is one norm which does not require any inner product. So it does not come from inner product. So although they are the standard norm which we know that comes from an inner product. So when we have an inner product, we have a norm. But there may be some norm which does not come directly from the inner product. That is what really important. That's why this norm is really important. Is it clear? So this example is just giving you an idea that there may be some norm which is not coming from inner product. Okay? Because for being a norm, we just need these 3 properties to be satisfied. Right? And there is no point of inner product. So by using inner product, we can define a norm, but all norms are not coming from some inner product. And that is one example.
Sir, is this
Yeah.
Cauchy squats coming? Means it is not covered in the lectures.
No, Cauchy squares I have, so basically, if you want to prove that this is a norm, which is coming from the inner product, this one, the standard norm, this one. If you have to check this is a norm, you require Cauchy square. That's why I have written here. If you have to prove this first property, this one, norm of x plus y less than equal to norm x plus norm y, for this one, for this inner product, this one, inner product norm, then you need Cauchy squares to prove that. Okay?
Okay, sir.
So that's why I have written it. Yeah.
So
Any
from,
doubt?
from
Yeah.
now on, uh, who will be taking? You will be means your team will be taking, or another team from calculus will take the sessions.
No, no, no. This we will take calculus.
Okay, because it is now we are from shifting from linear algebra to entirely some off-track new
No,
units.
that is not off track, as you can see. I mean, though it is multivariable calculus, but it requires linear transformation a lot, right? It will require linear transformation because. So let me give you an example before going to week 9. So you know tangent plane, right? Suppose you have a surface in R3. You know what a tangent plane will look like.
Heard of it.
Yeah. I mean, just suppose take this one. Take this one as a surface. This one. Now, if you at this point you will consider a plane. The tangent plane will look like this, correct? So basically, it is a plane like this, a plane like this, which is not passing through origin. So, do you know that any size subspaces of R3? We know, right? And these are called basically affine subspaces.
Yeah, affine spaces.
So basically, when we are dealing with tangent plane, we are dealing with affine subspaces, and that is really important in multivariate calculus. So we are not really going off track, but so there is a huge connection between all this.
Okay,
We'll see that.
thank you.
Yeah. Okay. So what we discussed today, I think more or less it is clear, right?
Yes, sir.
Okay, fine. So you can solve this now.
Yes, sir.
We can get it as